Hi everyone, and welcome to video number 8 of this series, in which we are learning how to model an end plate steel connection, which is this model that you see here. Before we get started, let's just set up some things here. So first of all, select from this drop-down list the Abaqus deck, so that you have access to these tools that are related to Abaqus. And in the draw mode, this button here, select PID, so that the visualization of the parts is as per their PID or property ID. And in the yellow buttons, where we control the visibility of cones and points, be sure that you have everything that I have activated here. And in this drop-down list, deactivate spots. I don't want to see spots, so that this model looks cleaner. And in the database, and by the way, it's important to have Abaqus deck selected here, so that you have the same structure as I have here for the database. Because, for example, if I choose Nastran here, you see that the database looks different. We have different items. So we should have Abaqus selected here, and then we have this structure for the database. And then in here, uncheck point and curve, so that points and curves are not visible, and our model is going to look cleaner. And I guess that's all we need to set up now. And well, before we start creating more entities and defining the rest of the mathematical model, let's do a quick overview about everything that we have defined so far. So we know that in here we are defining a mathematical model of the type boundary value problem that is going to represent this physical model of the real world, right? The first part of the definition of this mathematical model is the domain, which is what we have done in the first video of this series. We have created this geometry using the classic topo module, this module here. We created then these faces here. And then after that, we have discretized this domain. So in the classic mesh module, we have meshed these faces, so that we have divided these faces into finite elements. Well, this is one of the first steps in the solution procedure of the finite element methods, as we know. And then after that, we have created the bolted connections. So for these bolted connections, let me isolate here. We have this coupling connected to the end plate, this one, right? And then we have this beam element connected to the coupling. And then we have this translator connected to the beam. And the translator is also connected to the coupling that we have there. And the coupling is connected to the column flange. So here you have isolated all these items. And this is the bolt modeling strategy that we are using for this first run. And then in the next run, we are going to consider solid elements for the bolts, washer, nut, and etc. Okay, this is a kinematic coupling. This means that it's a rigid coupling. And the translator connector is used for bolt pretension. And by the way, we have already defined the bolt pretension. Inside the load group, we have connector load, and then we have this item here where we have defined the bolt pretension that is equal to 155 kilonewton. Now let me click on Show All to have everything visible again. And also we have defined the contact that we have between the end plate and the column flange. So we have here the contact defined, this contact here, and And we have used a surface-to-surface contact with a small sliding tracking formulation. We have also defined a friction here in the interaction. Press F2 to open it. And then we have a friction ID, F2, and then we have a friction equals 0.44. Let me click on OK, OK, and OK. So we have the contact. And we also have set up the step, at least step 1. We need to create one additional step, and we're going to do this in this video. So expand the step group, and then we have a step here, double click, and then we have this step, bold pretension, double click on it. And then in the previous video, I was explaining about this setup. We activated geometric nonlinearity, unsymmetric matrix storage because of the nonlinear contact. And in parameters, we have set up the initial increment as 10%, total, minimum, and maximum. And yeah, that's all we have done so far. Now let's continue then working on this model. The next thing that I want to do is, well, if we go back to this article that has the orientation about how we need to create this model. I'm talking about this article here. And by the way, you see that in the article, the author has modeled the bolts as solid elements, but it has modeled the bolts and the nut all together, like with a continuity in the nodes. I don't really like this modeling strategy, and I also don't really like the quality of his mesh. You see, in here we have some very bad quality elements. And also this mesh here is not really looking so good. So in here we need to find information about the boundary conditions that we need to apply. Let's see. So I have some information here. He's saying we have a displacement constraint in the column here in this region and also here. And we are going to apply a displacement load here in the beam. We also have this image. So this is in this article that has experimental data. And in this image, we can see the physical model. I guess I prefer to look at the physical model and decide by myself how we should represent this in our mathematical model. So you see that this is the column, right? The column is in this horizontal position in this case. And then it's fixed here where we have the stiffeners. Oh, sorry, I guess my camera is in front of it. So here we have the column. Let me deactivate my camera. We have this column here, and we have these stiffeners of the column. So it is these stiffeners that we have here, right? And then we have this beam above, and there is also something below. So this is fixed above and below. And the same thing happens here. We have it fixed below and above. There is also this drawing here that shows the same thing. We have something below and something above. So I guess that the best idea is to use this surface that we have here to fix this model, and also this surface on the back. And the same thing here. Okay. Yeah, let's do this. And well, let's start then doing this. Let me think here. Okay. So to fix this face and the back face, the first thing that we're going to do is to create a coupling. And in this coupling, I'm going to select the nodes of this face and this face. By the way, you see that I'm using this selection filter. First of all, if we want to select something from the viewport in the database, if we get some item here such as expand the element group and double click on shell, then I activate a selection filter for shell elements in the viewport, so I can only select shell elements. For example, if I try to select a coupling, I can't. And then in here, I can choose a selection mode. And then I have chosen this macro area option. And then when we have macro area, we can select these macro areas, as you see here. Okay, so this is a pretty interesting selection mode tool, and I use it a lot. So I'm going to fix these two macro areas and these two macro areas. I'm going to create a coupling considering these slave nodes as these nodes that we have here and there. And I'm going to let the software generate a control node on the COG of these nodes. So let's do this. Let's change here to Abaqus deck. And in the constraints group, we have coupling. Left click and hold, select nodes. And by the way, we have created a coupling using this procedure before, so let's use another procedure for you to learn a new one. Instead of selecting node here, I'm going to select set, but before, let's create the set. So simply close, and let's go to the set list here. And then I'm going to create a new set, right click, new, and new. I want to create a set of nodes. So in the database, select node, which in my case, it's already selected. And then in the selection mode, I want to select by area. I want to select by elements. So I can select, for example, if I select one element, I'm going to select all nodes of this element. So this is a good way to select nodes by selecting elements. So if I click here, you see that then I activate this mode where I can select elements. And then I can choose macro area. And then I'm going to select macro areas. So select this one, this one, this one, rotate, and this one. And then after doing this, if we press middle mouse button, this software selects the nodes of the elements that we have selected. And then in here, I'm going to say that this is the top column nodes. And then this is a N set, node set. Set is just a group of entities. In this case, it's a group of nodes, but it could be a group of elements, group of connectors, group of anything. Click on OK. And let's also create for this one, because we need here as well. Right click, new, select these 4 macro areas, middle mouse button, and then node set, and this is the lower column nodes. You see that after creating it, we can expand, and you see that we have nodes in this set. All these nodes here. Close the set list, and now we can create the coupling. So in the Abaqus deck, constraints group, coupling, left click and hold, and then select this option, set. And then we can select firstly the set that we have created, top column nodes, double click. And then middle mouse button to conclude. Oh, sorry, there is something here that I forgot. Let's press ESC and let's cancel. Now again, coupling, set. And then select this set, double click. And then we have these nodes selected from this set. Middle mouse button. Oh, okay, now it's correct. And then you see that the model browser opens, and then we should select a part to assign this new coupling. I'm going to choose here, for example, let me see, auxiliary entities, no. Connection entities. This is not really, we could put it here in the connection entities, it's okay, double click here. And then we have this card here that is for the coupling creation. Here we can choose a kind of coupling, distributing or kinematic. I guess that in this case, it's not going to really make so much difference, because you see, if we choose distributing, we allow these nodes to deform. We allow relative displacement between these nodes. And if we select kinematic, then we don't allow, it's going to be rigid. Since this is not a region of interest in this analysis, we are not interested in calculating stress here or anything like that, then it's not going to really matter so much in this situation. The region of interest is going to be really here, and the rotation that this beam is going to undergo. So in here, I'm going to then select kinematic, because kinematic is a kind of coupling that is easier to converge. Or we could say that it yields to less convergence issues. And then in here we have the reference node. You see that this reference node is this one that has been created on the COG of the selected nodes to be the slave nodes. And this is the ID of this node. If we select it and press F2, for example, I open the node definition card with the X, Y, and Z coordinates. Now press on OK to return. And then in here we have the surface type. This is a node-based surface. So basically, this coupling is attached to a surface that is created by the selected nodes here. So this is a node-based surface. Here we have the degrees of freedom. So this is these are the degrees of freedom that are going to be related to the reference node. So we know that everything that happens to the reference node transfers to the slave nodes. So if we apply a load here or fix this, then the slave nodes are going to be fixed. And then in here we have the degrees of freedom that are going to be related between reference and slave nodes. Here we have the node set that we used to define the slave nodes. Here we have the ID of the node set. Click on OK, and the coupling has been created. We can do the same thing here. You see that the coupling creation tool is activated yet. You see, we can see it here. We have it activated. And now we need to select a set. And then we have a list of sets. Scroll down and find this one. Double click. And then middle mouse button to conclude. And then select this part, connection entities. And then here choose kinematic, and the rest is very similar. Click on OK. Now let me show you guys, we can close these to deactivate the coupling creation tool. Now let me show you one thing, guys. If we go here to the constraint item in the database and expand it, you see that we have coupling. Double click, and then we have this list of couplings below. I can increase the height of these, and then we have all these couplings that we have created so far, right? For example, this coupling here that I have created as the first one manually, because just this one I have created manually. The other ones I have created by using the bolt tool, right? So this one here, if I double click on it, you see that the coupling card has this appearance, right? However, if I go to this coupling, so you see there is one important thing in ANSA. If I double click on coupling, I have the selection filter for coupling, so I can only select couplings. And to be able to select couplings from the viewport, I should have these activated, pick. Because if I deactivate this, you see I can select anything. So select this, and then I can select this coupling, and then this is going to be selected in this list. And then I can double click on it, and then you see that the definition card of this one looks different. And this is because this is a coupling defined on a set, and these other couplings is defined by selecting the nodes directly. We can, for example, this one, if we want to make this one be defined on a set, we can right click here, and then we can actually, if I right click from here, and no, yeah, it's right click from here and then change type, and then in here we can select coupling on set. And then we can click on finish. And then if we double click on this item, then we're going to have this card for this coupling. And we have this set that has been created automatically. I usually prefer this kind of card definition for coupling. And this is something useful for you to know, because if you, why this is important to have a coupling defined on a set. Because then if I want to change the coupling slave nodes, I just need to modify this set, which is the one with ID 20. So I need to go to the set list, search this one, and then I can right click, modify content, and then I can, for example, let me choose here to node, selection mode, entity, and then I can insert this node for this coupling, middle mouse button, close. And I see that now this node is part of this coupling, but I don't really want to do this. So let's use the undo tool, go click on this drop down list, and let's undo this set modify contents. Okay. So this is something that is useful for you to know. All right, now for these couplings, we need to apply a boundary condition. But we should apply the boundary condition on the reference node of the coupling for these two reference nodes, right? So to apply a boundary condition in the Abaqus deck, we have the boundary group, and then we have this item here, boundary. Left click and hold until we see these options, and then let's apply on it. Let's select a node to apply this boundary condition. So select this node, zoom in this region, and let's zoom in a lot. And then you see that there is an issue here. There is this node here of this coupling, but there is another node approximately in the same position that is part of these four elements. So I'm not sure which node I'm selecting here. So what we can do is, let's select this node, for example, left click, middle mouse button to conclude. And then we have the node ID here for this boundary condition. Later, we need to check if this is actually the node related to this coupling. We're going to check it. But let's do this later. Here we have the boundary card. Here we need to define the step. Now, in Abaqus, if we define the step as 0, remember that in the Abaqus CAE application, when we remember that we had that initial step that we could use to apply boundary conditions that prevents rigid body motion, right? So that initial step is the step 0 here in ANSA. Okay. We can apply this boundary condition on this step if we'd like to. Let's do this. Let's apply on the 0th step. And this is going to be could be a displacement, but you see that we have also fixed. Since we are going to fix the displacement degrees of freedom, we can choose fixed. But if we choose displacement, well, let's do one thing here. Let's choose displacement at first. And then in here, we can choose the degrees of freedom that we want to prescribe a displacement. Let's remember that this kind of boundary condition is named as essential boundary condition. And this is to prevent rigid body motion. And then the stiffness matrix of this assembly is not going to be symmetric. And then we have a unique solution for the active displacements. Okay, this is just a note of something that we have learned in the theory part. Now, what are the degrees of freedom that we are going to fix? If we go back to this image, you see that this restriction here kind of it fixes all translational degrees of freedom. Looks like it fixes. I don't know if we have some welding here or something. We don't have all the information that is really required. Let me deactivate my camera, sorry. We don't have all the information because we don't know actually what happened here, if we have a welding or something. But I guess that we have all translational degrees of freedom in here fixed. And for the rotational degrees of freedom, let me take a screenshot of this and put it here because I need to create some drawing. Let me get my board. So let's look at this one that is visible. For the rotational degrees of freedom, if this column tries to rotate like this, then this beam and this is going to kind of prevent, not completely, this kind of rotation. So we have some type of connection that doesn't completely allow this kind of rotation, but doesn't completely restrict this kind of rotation. We have something in between. It's like a flexible a flexible attachment. But in here we need to choose, well, we obviously can model a flexible attachment in ANSA, but it's not really worth it to do this because it's not going to impact in the results of this simulation. Or actually, this is something that we're going to know when we run this model. If we have the simulation results not matching with experimental data, then we know that there is something wrong with the mathematical model, and then we should check. Well, maybe this is related to how we defined this boundary condition. Anyways, we need to check many things in the model to see what is yielding to wrong results. But in here we need to decide some things. We need to simplify some things because, you know, this is a simplification. The fact that we are not representing this beam and this beam, because instead we are applying a boundary condition. Remember that a boundary condition is always the representation of an external entity that is not being represented. So a boundary condition is a simplification. When we are creating a model, we need to consider simplifications, and we should be careful. And we should remember that we had defined these simplifications, because in case we have simulation results not matching with physical experimental data, then we should remember where we have simplified the model so that we can maybe create something more realistic. Now, if we talk about torsion of this column, that is rotation about its own axis, I guess that the way that it's fixed here, it's preventing this kind of rotation, right? And now let me think about rotation about. So if we get here, okay, let me create it like this. So here we have the eye shape profile, right? And then we have talked about rotation about this axis, right? And now if we think about rotation about this axis, it's hard to create this drawing here. It's like a rotation about, yeah, this doesn't look so nice, but you know, a rotation about this axis here. This also prevents this kind of rotation. I don't know if I have a welding here, but if imagine that we have some welding here, and then this is going to prevent some rotation. Anyways, let's just assume that it's going to prevent rotation. So in here, this means that I'm going to fix all degrees of freedom. 1, 2, 3 is translational displacement. So displacement in the x direction is 1, displacement in the y direction is 2, and etc. And here 4, 5, 6 are rotational degrees of freedom. So 4 is rotation about x, 5 is rotation about y, and 6 is rotation about z. This is related to the global coordinate system that we have defined, where you can see the global coordinate system here. Okay. You see that for these degrees of freedom, we are creating a prescribed displacement equals 0, and here we can define this value. And this value can be non-zero as well. But in this case, it is equal to 0. And that's why, let me just return here. That's why instead of applying a prescribed displacement, we could select fixed here. And then we select the degrees of freedom, and then we cannot select a magnitude because it's going to automatically be set to 0. Okay? All right, now let's click on OK. And let's do the check if we have applied these to the correct node. So how do we do this? In the constraint item, double click on coupling, select this coupling. Be sure that you have peak activated. And then we have it selected here, double click. And then this coupling has these as the reference node. I'm going to Control C, this ID. It ends with 88. Click on OK. And then let's search for this item in the database, which is a new item, boundary, double click. And then we have this item, double click here. And then we have the ID of the node that was selected for this boundary, which is 24288. I can Control V, the ID that I have copied previously, and then you see that it's the same ID. Okay, let me erase this. So this is correct. Click on OK. Now we should do the same thing for this node here. But, you know, since it's going to be the same boundary condition, instead of applying two different boundary conditions, we can create a set with this node and that node and apply the boundary condition on the set. So let's do this. First of all, search here, constraint, coupling, select this coupling and this one. And in this list, right click, again, double click, select this coupling, and in this list, right click and show only. Now go to set list, right click, new, select node here, zoom in, select this node, zoom out and zoom in here and select this node. You should have selected two nodes, middle mouse button, and then this is a node set. I'm going to name it as fixed nodes and click on OK. And then close the set list. Let's return to this boundary condition that we have created. Double click on this item. And then you see that we have that node here. Instead of selecting by node, let's change it to set. And then select this field, use question mark to open a list, select this set that we have created, fixed nodes, double click, and then click on OK. Now we have the boundary condition applied on both nodes. Click on show all, and let me see, 35 minutes. Okay, now let's apply the load that we have here, right? You see that in the physical model, we have the load applied by this hydraulic actuator. And then there is a load cell here to measure the load that is being applied, right? In the mathematical model, you see that we have displacement load. So this is something that is very important, guys. Let me talk about this in here. We have two kinds of boundary conditions, right? We have the natural boundary condition and the essential boundary condition. Essential boundary condition are prescribed displacements, which is what we have done here and here. Natural boundary condition is related to traction or, for example, body force. Body force is a force that acts throughout the whole domain of this problem. And by the way, this is something that we should have. We should have gravity, which is a kind of body force. Because obviously that in the physical model we have gravity, but probably it's not going to make so much difference. Maybe we could even simplify this by not applying gravity, but let's apply gravity because we are going to learn how to do this and it's interesting. So natural boundary condition is related to traction and body force. Remember that traction is a force per unit area that we apply on a outer boundary of the domain, right? Traction could be, let me get here and create this drawing. It's important to remember about some things that we have learned in the theory. So we have the domain, right? And then we have some prescribed displacements on some regions in the outer surface of this body. This is essential boundary condition. And then we can also have traction, which is the natural boundary condition. So for example, imagine that I have a traction vector here, and then there is a normal unit vector facing in the direction outward direction of this surface, right? And then this traction is going to have a component in the normal direction, and it's going to have a component in the tangential direction. This traction can yield to a tensile normal load, or even we can have a traction like this, which yields to a compressive normal load. And the other component is the shear component. Okay, this is the natural boundary condition. And I'm explaining this to you because it's easier to make this model converge when we have only essential boundary conditions. Natural boundary conditions yield to more convergence issues. So if we apply here a force, we're going to have more convergence issues than if we apply a displacement. And remember that a displacement acts like a force, because if we apply a displacement, we're going to have a reaction force, right? So whenever we can, instead of applying force, we can apply displacement, and that's what we're going to do here. And the result is going to be the same, but the convergence is going to be easier. Okay, the idea of this model is to calculate a curve like this, moment versus rotation. So the idea is that we need to apply a displacement here at the tip of this beam in the downward direction, a large displacement, so that we can create a plot like this. It doesn't matter how much displacement, it matters that it should be a large displacement so that we can create all this curve. Because if we apply a small displacement, maybe we're going to just create the beginning of the curve, you know? So this should be large enough so that we reach this position here, for example. Okay. All right. So let's do this. Let's look at the physical model. And well, by looking at this image, I see that most of the force is going to be on this side, right? We have also displayed on the other side, and there is contact here and all, so there's going to be some force acting here. But I don't really think it's. I think it's worth to consider that we have the force applied on this region. I'm talking about. Let me double click on shell macro area. I'm talking about this macro area here. Right, we can create a coupling here and apply the load, the displacement at the reference node of the coupling, just like we have done here. Instead of also creating a coupling here, I don't think this is necessary. Creating here is a good representation of what is happening here. All right, so let's do this. So go to the Abaqus deck, coupling, left click and hold nodes, and then we should select the slave nodes. So select this mode here to select elements, macro area, select these 4 macro areas, middle mouse button again, and then it's going to create the reference node on the COG automatically, middle mouse button. And then I want to create, well, it could be a kinematic coupling as well, because I'm not really interested in what happens here. So we could consider this phase to be rigid. We are not interested, for example, in these stresses in this region and nothing like that. We are interested in calculating the rotation that we are going to have in this region. Okay. And then for parts, we could select ask always, all degrees of freedom, and then finish. And then here we should select the part. So let me drag the model browser by using the left mouse button like this. And then let's select connection entities, double click. And here we have the coupling created. Close. And I want to apply the displacement, the downward displacement. But the thing is, we need to create one additional step for this. You know, because we should apply this displacement after the bolt pretension is applied. So let's do this. Before we create this new, actually, I was going to say that we should define the output requests, but no, let's do this after we create this step. So let me talk about the step manager. So let me see how much time I have left. Well, I have 20 minutes. Yes, I guess we have time. Let's go to the step manager. The step manager is very important. Here's where we manage the steps and the boundary conditions in the analysis. Double click here, and then we have one step manager defined. Anonymous step manager, double click, and then this appears. Let's increase the size, and this is good enough. You see that we have one step created in this analysis. This one here is like the initial step, this one. If we expand it, you see that in this one we have a contact definition, which is this contact, and we have that boundary condition that fixes these nodes that we have defined in the 0th step. So it appears here. Now, if we expand the step 1, let me increase this column. We have only the connector load that we have here for the bolt pretension. this boundary condition that has been created here is going to be propagated to this step automatically. Okay. Now, I need to create one additional step, and to do this, we could click here in new, but instead of doing this, we can copy this step so that we're going to use the same configurations, which is a good idea. So right click here and then copy, and then I can copy step or step and conditions. I don't want to copy conditions because then I'm going to copy this connector load. So I just want to copy step. Okay. And then let's give it a name. And in here, I'm going to give it as the following name, load step. Oh, sorry, load step. Because this is the step that we're going to apply the load. Downward load / displacement. We could do one thing or one of these two things. The result is the same. At the tip of the beam. The ID is 2. Large displacements nonlinearity activated. This is important. Unsymmetric matrix storage. The parameters are set up already. We're going to use the same static solvers. So we have the governing the equilibrium governing equations, which are those 3 differential equations. We're going to define the output requests later. And that's all we need. We don't need to do anything here. Let's click on OK. And you see that now we have this additional step, but there is nothing inside this step. There's nothing defined here. So let's close the step manager and let's go to Abaqus deck. And in boundary group, we can apply a boundary, another boundary condition. But just as a curiosity, if you'd like to apply a force instead, you see that in the loads group, we have this C load. The C load means concentrated force. Left click and hold, click on node, and then zoom in, select the node, middle mouse button, and then we have the C load card. In here, you should say that it's in step 2, that we should apply this load. This is the node ID. And then it's in the Z direction, right? In the vertical direction here, look at this coordinate system. And then we have the magnitude of this load. But we are not going to do this. So click on cancel. And then we are going to actually apply a boundary condition. So boundary nodes and zoom in. And you know, this is a little confusing. So instead, press ESC. Double click on coupling, select this coupling, and then in here, right click and show only. Then Abaqus deck boundary nodes, zoom in and make sure that you're selecting the correct node. Middle mouse button, and we need to check if this is the correct node later. 24, 324. Second step. And then this displacement is going to be in the 3rd degree of freedom. That is displacement in the Z direction, which is this direction, and in the negative Z direction. So we should define here a negative displacement. Let's define it as -200, for example. I don't know if this is enough. Let's test it out. And then click on OK. And click in show all. And that's all we need to do. Okay. Maybe we are going to face convergence issues because maybe we will need to fix the displacement here in the Y direction, in this direction. And maybe sometimes we need to fix torsion as well. Let's see if we're going to face any convergence issues, actually. And by the way, this tool here, this attachment, you see that it creates some stiffness against torsion of this beam. and also some stiffness against some displacements in the direction normal to the plane of the screen. So that's why I'm saying that maybe we need to do this as well here. But let's firstly run it as is, as you see here, and then we can work on it. Okay, let me think here. Now we have defined the boundary conditions of this model. This is part of the mathematical model, as you know. Okay, let's think about it. Remember that boundary value problem, which is the type of mathematical model that we are defining, is defined as governing equations defined in the domain. And then we have those 15 equations. We have the stress-strain relations, we have the strain displacement relations, and we have the equilibrium equations. Those 3 differential equations, right? This is equal to 15 equations. We have defined these already because we have defined the kind of element formulation, which is S4 and S3, and we also have selected the static solver. So when we do this, we have defined all this information, right? And then here we have the assumptions considered. So we have activated the large displacement nonlinearity, right? So we are going to allow large displacements. We have the large displacement algorithm being considered. We have material plasticity being considered and everything else. The other part of the BVP definition is the boundary conditions, right? And we have just finished defining these boundary conditions. Okay, so basically, we have finished defining the mathematical model that is representing this physical model. There is just, let me see if we have time. Okay, we have some time. Let's go back to the step manager, double click here, and then let's open up the step manager. And you see that in the second step, if we expand it, we have this new item, boundary, which is the boundary that we have created. Notice that the boundary that we have created in the 0th step, here in model data, this one, has been propagated to this step and also this step. Okay? So we don't need to redefine this. What we need to do here is to fix the bolt pretension that we have applied on the second step. This is another boundary condition that we need to create. So we didn't finish yet. We haven't finished yet the definition of the boundary conditions. So let's do this. So what is the idea here? Let me create this drawing. This is very important. Imagine that in here, I have a coupling. I'm going to create this drawing here just for you to understand. I'm going to create this drawing that is composed of this coupling and this connector. I'm going to create a drawing with this view like this. So in here we have the left coupling. In here we have the right coupling, right? In here you have the beam. And in here you have the translator connector, right? Let's suppose, I know that the translator connector doesn't have a length now because we have matched the position of both nodes, but let's suppose that it has this length here, right? Now we apply the translator connector load on this translator connector, right? And then this connector load is going to move these nodes in this direction. And so when this happens, this beam is going to be, well, we are going to have a tensile load occurring on this beam, which is the bolt pretension, right? When we define the connector load as 155 kilonewton, the software is going to do the following. The software is going to try to move this node in this direction and this node in this direction until the reaction force produced by this movement is equal to this force. Okay, so the software applies a displacement, a relative displacement at these nodes in the direction 1, because we have defined it here. Direction 1, x1, in the axial direction of that coordinate system. And then it calculates a reaction force that this displacement produces. And then it does that until this force is reached, right? Now, in the second step, we need to fix this. So we need to fix the relative, we need to fix the displacement that the software produced to reach this bolt pretension. Okay, we need to fix this displacement. So let's go to the Abaqus deck, and then in the boundary group, we have the connector motion boundary condition. Left click and hold and select set, because we have a set with all connectors. And then let's scroll down, and this is the set, bolt pretension connector. This set has all connectors. This is the set that I have used to apply the bolt pretension. So double click on it, and then this is going to be applied in the second step on this element set. And in here, we are going to select fixed. And this is very important. The degree of freedom is 1. So in here, we can't select displacement. We should select fixed. Because displacement, we are going to define a specific value for prescribed displacement, but we don't know this specific value because the software has moved the nodes, but we don't know how much. So when we use fixed and 1, we are telling the software, whatever the displacement you have, fix this displacement in the x1 direction, which is this direction here of this coordinate system that you see, the x-axis. So fix this relative displacement. Okay, so this is the meaning of this boundary condition. It's very important to understand this well. Okay, now click on OK and close here. Now let's go back to the step manager, open it. And now you see that in here we have this new boundary condition created. So let me increase the length of this column. Connector motion. We have this new item here, right? Now the thing here is, now that we have this connector motion, fixing the relative the relative position between the nodes of the translator, we don't need anymore the connector load. So in this step that we have the connector load, we don't need anymore this connector load in the second step. But this is being propagated to the second step automatically. So we need to tell the software that we don't need it anymore. So we're going to double click on step 2. And then you see that in here we have reset conditions, which is an OP equals new function. I can left click in here and select connector load so that we are resetting connector load in this step. Click on OK. Now this connector load is not going to be propagated to step 2. This connector load is going to be substituted by this connector motion. Okay, that's what we needed to do, and we're going to use the same strategy when we get to model this using solid elements. Okay, this is very important. You should understand this very well. Okay, let's see. 1 hour. Well, we have some time yet, so let's define the output requests, and then we are going to be finished. In the next video, we can run this module and post-process the results, and then create these graphs here to compare with what we have here, and it's going to be very interesting. And we can also compare these images and etc. So to define the output requests, we can define it by using step 1, and it's going to be extrapolated, not extrapolated, but it's also going to be used in step 2. So we don't need to define for both. We can only define for one of them, actually for the first one. It's going to be propagated, that's the word. Double click here, and then go to output requests. And well, let me tell you guys that at first, when I started using this, I thought it was very confusing, the output requests. I didn't like it at first. But after you understand it, you're going to start liking it. Okay? First of all, let's open up the Abaqus manual. Let me see. I wanted to show you a list of output requests. Yep, output is here in the first one. You don't need to have this PDF, you can simply search it on the internet. So in here we have output variables, item 4.2. In here we have a list of outputs and the explanation of what is each one of these output requests that we can select there. So let's go back here to ANSA and let me explain to you how it works. First of all, we should select from this drop-down list. The first thing that we should select is this option here, output. I guess the best idea is to show you a file that is ready. Let me show you, let me get here from this, any file that I have here, could be this one, this .inp file. And then let me scroll down, let me search for a step. And then in here you have the definition of a step. And this is the region in the .inp file that we have the output request. So you see that in the first line we have this command, output, and then this is a field output request, which means that it's something that is going to be calculated for all nodes or all elements. And anyways, we know well about it. So the first thing that we need then is this command. And we should choose here if it's a field or history output request. So at first I want to select field. And then we can choose other things here. It's not going to be really necessary in this case. So simply click on insert. And then we have this new row here, right? So the software is going to write this first row in the .inp file. Now we need to go to the next row. So let's define here this option here, node output. In here we can select results that are calculated on nodes. And in this case, since this is a field output request, this is for all nodes in the model. To select it, click on identifying keys, and then we have the nodal variables, increase these, and then we can search by letter. Let's start with displacements, and it's going to be in letter U. And then I want to calculate translations and rotations. So check this box. And also go to R, expand R, and I want to calculate reaction forces. Actually, this one is better. Reaction forces and moments, RF. Okay, so check this box, and that's all I want for nodes. Click on OK, and click on Insert. And then we have this new item created below the output. So ANSA is going to write this, exactly what we have here. It's going to write this. So this is a field output request calculated on all nodes. And then in here we have reaction force and displacement. Obviously that reaction force is going to be calculated only where we have prescribed displacements. And not in all nodes in this case. Okay, the next thing that I want to calculate is element output. So these are things that are calculated based on elements. And then in here we can click on identifying keys. And then let's search for S. And then in S, select stress components and invariants. And then in here we can calculate all the stress components, all the 9 stress components, or 6 because it's symmetric, and also the invariance. So we can calculate the von Mises stress, for example, which is an invariant. But we can also calculate other invariants that we have learned previously. We can also ask for this option here that is very important. In P, there is equivalent plastic strain. So this works like a von Mises stress, but for strain, for plastic strain. Okay, in this model, since we have a perfectly plastic material model, oh yeah, we are going to have very large plastic strains, but because the stress doesn't increase. But anyways, let's calculate it and check it in the model. I'm going to explain more about it when we get to calculate it. Let me think here. I guess this is good enough for this model. Let's click on OK and insert. Now we have this new item, and this is going to write something like this. S is for stress, but we are going to also have something like this, PEQ and comma. Okay. Now, if we'd like to calculate history output requests, then we would need to create one additional line here, but we need to actually, this is something that we need to do. We need to create a history output request to create the curves that we need to calculate. But I will need to spend some time explaining how we are going to calculate this rotation that is going to be used to build these charts that you see here, these charts, how we are going to calculate this rotation, right? So I need to spend some time, and this is going to be defined here as a history output request. Okay, so let's do this in the next video. So for now, let's just ask one additional thing related to field output, which is a contact output request. So in here, search for contact output, identifying keys. And guys, in the Abaqus users guide, we can check some things related to contact, such as, for example, if I go to letter C, you see that we have so many options here, right? We have a description here of each one of these options. So for example, this one here, there is one here that is very important, which is the C stress. Oh my God, it's always hard to find it. C stress, contact stresses. This one is very important. You can Control F and search for C stress here, and in the Abaqus users guide, you're going to find it. Let me press enter until I find the one that I wanted to show. So mechanical analysis, nodal quantities, stress, contact pressure, and frictional shear stress. And anyways, we have a more detailed definition of this output request. And in here we also have this other definition. And anyways, you should always have the Abaqus users guide opened for you to check. Just 1 second here. So for the contact, we can define. We're not going to really use so many. We will not need to really read. I mean, we will not need to check so much the contact, because this exercise is not going to yield to convergence issues for the contact, I guess. But there are some outputs that we can request, such as C status to calculate contact status if we have contact, if it's opened. There is this total area in contact, contact displacement. There is also total forces due to contact pressure. This one is interesting. Anyways, there are so many kinds of output requests that we can request here. If in your case you have something that the focus is in the contact, then you should get here from the Abaqus users guide and search for the outputs that you have available and select the one that you need. Okay. So for this one, let's select what I have selected here, click on OK and click on Insert. Now we have this new item. And it's below the field output, so this is a field output request. All these 3 items are field output requests. Click on OK. And let's close this. Click on Show All. And let's save this module. And guys, that's all I had for this video, and in the next one we are going to finally solve this mathematical model using the finite element method. So I hope you liked it, and see you in the next video.